Welcome everyone to Pint of Science 2021. I'm Vino and this is Nicholas. And today we're your hosts. We're going to take you on a journey to explore the extremes of planet Earth, ice and fire. We have two very exciting talks to get your little grey cells tingling. Stick around till the end. We have a Q&A session with both speakers. If you have any comments or any questions, please put them in the comments section and we'll get to those at the end of today. But we could not talk about our planet Earth without mentioning one of its greatest advocates, David Attenborough. Did you know that David Attenborough was rejected from the first job he applied for as a radio talk producer for BBC? But like many scientists, he babbled on, and now we all know his charming voice and charisma. So today we're going to test how well you really know the man. So if you head to www.menti.com, we have a poll for you. The code to enter is 24287581. And today we're asking you, which of the below animals are named after the famous David Attenborough? You can select as many as you like out of Matapesis attenboroughi, Plesiosaur attenborosaurus conibere, Brachiosaurus attenborosaurus, Masterpieces attenboroughi, Electrotetics attenboroughi. I hope you have more luck than I did with the pronunciation of those words. So we'll leave you to ponder the poll as we move to our first speaker tonight. Over to you, Nicholas.
Thank you, Vino. Today we are very lucky to have Dr. Michel Tsamados. He's a lecturer in polar observation and modeling. His research is always intended to address practical challenges in the field of material sciences and climate sciences. He's now going to talk about his field trip to the Arctic. Thank you so much for joining us this evening. Michel, please take it away.
Much, Zina and Nick. Thanks. It's a great honor to start this amazing series of lectures. So today I'm going to talk about we are in the ice. So this is a self-quote I made in the Arctic as part of an expedition I took part in last year. And it's a kind of expedition through the Arctic and also through climate change. So I'll tell you about this. But first, I encourage you to sign up to Mentimeter. I'll ask you a few questions. The first one is, what does sea ice really invoke to you? So you can go on Menti via your phones. It's the red one, so apologies for the number at the top. And enter any ideas, any suggestions that come to mind. We'll come back to this at the end. So I want to show you a schematic. So I did a bit of drawing here. And this is an illustration of what sea ice really is. It's the frozen ocean in the Arctic in that case. Here I'm showing it at the end of the summer when most of the ice has melted. And this is a typical extent of ice in white. You can see the UK for scale. At the end of the winter, the ice grows again, and it has a much larger extent. Again, you can see it here in white. The Arctic sea ice is a frozen ocean. It's a Mediterranean ocean confined by the Russian continent, the Greenland, and North America and Canada. So I've got a little question for you: is how do you think, how large is sea ice? And in terms of and to help you a bit, I would like you to think in terms of how many UKs. So the first question I will have for you is trying to think of how many UKs is the ice in terms of area at the end of the summer. And then try and think also how many UKs it is at the end of the winter at its maximum extent. So this is the first question for you on Mentimeter. Have a go. Guess, is it 1 UK, 5 UKs, 15 UKs? Have a guess. The UK is on the map to help you out. Try also in the winter at the end of March. How many UKs is it then? Is it 10, 50, 60? Have a guess again. We'll check your answers at the end of this talk, but just to give you a sense of how large the Arctic is. And this is a very two-dimensional view of the Arctic, right? So the Arctic sea ice. A lot of satellites give us this two-dimensional view, but what about the third dimension? This question I always ask my students or in talks: how thick do you think is the sea ice? So I'm going to call the thickness T here. So have a little think on Mentimeter again. Is it 10 centimeters? So I'm asking you an order of magnitude. So we do that in physics. a multiple of 10? Is it a power of 10? 10 centimeters, 1 meter, 10 meters, 100 meters, or 1 kilometer? When I ask this question, most people get it wrong, so it's quite fun to look at your answers at the end. So what I can tell you is that the sea ice thickness is, I did a little drawing here showing that it's not homogeneous, right? So there is a gradient between Greenland and Canada and the Russian sector. And essentially the ice is piling up under the influence of the winds and the currents against the coast of Canada and Greenland, where it's at its thickest value. On the bottom right corner, you see something that is an amazing result from a satellite we contributed to develop called CRISAT-2, and we're now able to measure this thickness. So have a think about how thick sea ice is. We'll come back to this at the end. So this is a little animation showing the results from this satellite CRISAT-2 that is really like wearing 3D glasses. For the first time, we were able to measure from space, thanks to this altimetry technique, the whole of the sea ice thickness. So this was the holy grail of polar remote sensing, and we have now achieved that. So I'm going to move on. So we have 10 years of data of that type. So we've got this picture of Arctic sea ice as a kind of gigantic ice cube shown here. So I'm going to ask you how much ice there is in total. What's the total volume? My image here of this ice cube is quite misleading, because really the ice is like a very thin cover of ice with an aspect ratio of 100,000. So it's 100 times thinner than it is wide. So that helps you think about the magnitude. So try and think how much total volume of ice there is, and use meters and kilometers in a consistent way so that you get your calculation right. So the Arctic sadly has changed dramatically over the last
20 to 30 years ago. The sea ice covering the Arctic.
You don't need the voiceover. So the Arctic has changed dramatically over the last 40 years, as shown here from some NOAA results. In white, you see the very old part of the ice, which is not that old, it's only 9 years old. And you see that from 1990 all the way to 2020, the ice is getting younger and younger for two reasons. First of all, it's exported through the Fram Strait, northeast of Greenland, but it's also melting more and more. So what has happened is that over the last 20 years, we've seen a dramatic transition of the ice, going from an older multi-year ice cover, very white, to something very blue here, which is ice that's almost entirely first-year ice or second-year ice. You see this dramatic loss of ice due to melt events in 2007, for example. So in a way, you can argue that sea ice has already completely disappeared if you characterize it as old multi-year ice. And that's the effect of climate change and climate warming. Compare the dramatic picture here in only 36 years. So this is also true when you look at the sea ice extent from 79 to 2020. You see that we lost about half at the end of the summer of the total extent of sea ice. So I'm going to ask you another question for Mentimeter. And this is, when do you think September sea ice will disappear? Has it already completely disappeared? Will it disappear in 5 years, in 2025, in 2050, or in 2100, or maybe never? So I would like to see what your guess is about that, or what your knowledge is about that. And actually, like it's often the case in science, many answers are correct, really. So don't be shy. You're almost guaranteed to be correct in one way or another. And we can discuss that. So I did another little drawing. I drew London with a Shard and Big Ben and Parliament and Regent's Park and so on. And I put the first ice cube here at the bottom left. It's a tiny ice cube of about 50 by 50 by 50 meters. Then I put a bigger one of 200 by 200 by 200 meters, 500 meter wide, 1 kilometer wide, and 2 kilometers wide, to give you a sense of how much sea ice there is in total in the Arctic. One of these 5 ice cubes is correct. So try and guess again on Mentimeter. Is it A, B, C, D, or E? Bearing in mind that the bigger one is 2 kilometer by 2 kilometer by 2 kilometer, and is roughly to scale with London, roughly. I didn't use a ruler or anything. So But again, this ice cube picture is quite misleading because the ice, again, is a very thin layer, so it really covers a wide area. Anyway, why did I talk about this ice cube? The reality is that this ice cube is really what the expedition, the scientific expedition mosaic I'm going to describe, was really doing. Essentially, we went on this ice cube all the way to the North Pole and drifted with this ice cube for an entire year. And why did we do that? We wanted to understand the physics of this ice cube. So this is an experiment you can do in your house. I did it with my son. You put an ice cube in a glass of water, top left, and you calculate how long it takes for this ice cube to melt. Then try and blow warm air on top of it and calculate again how long it will take for this ice cube to melt. Now, if you put fresh water on top of it, flowing water on top of it, again, how long will it take for the ice cube to melt? Put it in a glass full of water, and again, how long will it take to melt? Then blow air on top of this ice cube, calculate the time. And finally, if you add some salt, what will it do to the process of melting? Which of these do you think is going to melt the fastest? Try the experiment at home. It's a simple but very fun experiment. And this is quite a complex problem. A lot of physics happens. And this is exactly the kind of physics we studied in the Arctic. And the physics of the coupling between the air, the ice, and the ocean is essential to understand the fate of the sea ice and to understand also our climate, the changing climate and climate change. Sea ice, because of its reflective role, reflects it's very white and reflects a lot of the incoming sunshine. So as the ice is melting, it contributes to the positive albedo feedback, and really it contributes to 0.3 degrees additional warming by the end of the century. So it's an important part of our climate we really need to understand. So this mission was this German-led mission, but an international expedition, where we froze an entire icebreaker called Polarstern into the ice, and we drifted with the ice for an entire year to do this kind of experiments I showed you on the ice cube, but this time on a giant ice cube. So this is a little bit of an explanation in a video. This is an icebreaker, and what we did is we mirrored the expedition that Nansen and some other Russians did throughout the 20th century and late 19th century, which is to go to the Russian sector of the Arctic and drift with the ice for an entire year. So I was very lucky to be part of this expedition, the first part of this expedition. And here is a little illustration of the kind of experiments we did. So we deployed a lot of experiments on the ice, on the giant ice cube. The icebreaker turned off its engine and really just drifted with the ice. And this is some of the experiments we did. We looked at under ice processes, how the ice is melting under the ice. We looked at the top of the ice. We looked at the characteristics of the ocean all the way down to several hundreds of meters to understand the salinity and the processes at stake. And we look at the atmospheric process as well. So this is a kind of schematic of all the science we did on the ice. I was very fortunate to be on the Russian icebreaker, the red vessel on the bottom right corner here, called Fedorov. And now for the next 5 minutes, I'm going to tell you a bit more about my 6 weeks on board the Arctic, the Akademik Fedorov. I was on board this vessel with 100 scientists, students, and educators, and 150 members of crew from the Russian equipage. So we left Tromso, north of Norway, in late September 2019. And really, what is amazing about this trip is that we crossed possibly the most emblematic region of climate change. This red region here is the region that has experienced the most dramatic impact of climate change. Almost half of the ice has melted in this region of the Barents Sea, North Atlantic, in only 20 years. If you look at temperature change, we have up to 6 degrees warmer temperatures in only 2 decades on yearly averages. So we really did a kind of back to the future trip through climate change on board our icebreakers. And indeed, we saw that the ice was very thin, thinner than we've ever recorded before. So we left Tromso on the 19th of September 2019. This is a little footage of that day. a rainy Norwegian day, and we left Norway behind us for 6 weeks. About a week later, we reached the ice. And this is really the point where I said, we are in the ice. I announced that. I have the claim that I was the first to see the ice, but maybe others won't believe it. And I'm definitely the first Greek to have seen the ice on board. And we were really treated to this beautiful sight, reaching the sea ice and really penetrating into the ice, you can see here. And I even made it into the US journal, thanks to my journalist friend, Chelsea Harvey, who wrote a piece about that. So that's the title of my talk today. We are in the ice. We carried on in the ice, and sometimes later we got stuck in the ice. The reason is that this icebreaker, the red vessel here, was not really an icebreaker. We were missold this as being an icebreaker, but actually it was only a consolidated vessel. So it cannot break through ice that is thicker than 1.5 to 2 meters. And what we saw is that one evening, the Russian captain had to break through the ice and go back and forth about 20-30 times in order to finally crack the ice and open a new passage to carry on to the North Pole, or further north. Further down, a few days later, we were up for a real treat. We met the locals. So we met a mom and a cub. This was a real photo one of us took. And then the little cub was playing with the ice cubes like, my son used to play. But trust me, nobody wanted to go on the ice at that point. We were all safe on the vessel because this beast can be quite aggressive. So, but it was really humbling, and in a way, it made me realize that this is also a place for life and for species such as this emblematic, beautiful beast here. A few days later, we finally reached our destination, the so-called castle. The castle was the name we gave to this thicker ice. You see these black blobs here on the satellite imagery. So we were looking for ice thick enough to not melt for the entire duration of the year and the mission. So this was very difficult because the ice was so thin due to climate change that it was really a challenge to find an ice thick enough to host all these experiments. So we finally found a piece of ice that we named the castle because of its shape here, you can see from the satellite image. Our job and my job with others on board was to contribute to the so-called distributed network, where over a radius of 50 kilometers, we took helicopters, we took skidoos, and we went to deploy instruments in a radius of up to 50 kilometers. So this was to give us a sense of the ice over a wider area around the polar stern. And this is my student, one of my students, Robbie Mallet on the left, measuring the snow thickness, which was really the core mission for my experiment, measuring the snow thickness and the interaction of the snow with the satellite instruments. And you can see that the measurements are quite fun. These are two students doing experiments and taking a magna probe and measuring the snow depth. And then the other student behind is measuring the ice thickness with an electromagnetic device, and seems quite confused. But she's very concentrating on getting the very accurate measurement here. And finally, and sadly, after 6 weeks or 5 weeks, we left the ice and we reached the open ocean, and we said bye-bye to the ice. And we came back to a world of COVID and people and other challenges. And it was a really transformative trip for me personally, but also to understand for the first time the sea ice and to step on the ice. So maybe we have time for questions now or at the end, and also look maybe at a bit more at your Mentimeter answers, and I'm happy to take questions. Thank you very much.
Thank you, Michel, for a very exciting talk with the amazing drawings. I'm sure a lot of us will want to be your student right now or take your module. Before we warm up with our next speaker, for those who join later, we have a little poll to test your David Attenborough knowledge. Remember, you can always have more than one answer. Please introduce us to our next speaker, Vino.
Thanks, Nicholas. So our second speaker today is Ryan French. Ryan is a solar physics PhD student at the UCL Mallard Space Science Laboratory and a Newkirk Fellow at the NCAR High Altitude Observatory. In his research, he uses space and ground-based telescope observations to probe the dynamics of energy release in solar flares. Ryan is also an active science communicator, routinely working with schools and the public to educate topics in solar physics and astronomy. Thank you, Ryan. We're really looking forward to this.
Great. Thank you so much, Vino. Okay, fantastic. I think everybody can see my screen, so I will get going. So the Earth is not a bubble, okay? We're sitting here in space. We're influenced by the near space environment, and the largest influencer of that environment is the sun, our local star, the object which the Earth and all the other planets orbit around. Now, although the sun sort of seems constant and unchanging in the daytime sky above us, it's actually incredibly dynamic. Its surface, its atmosphere is changing and churning over time frames ranging from seconds to hundreds or even thousands of years. Now, here I have a picture on the left of the sun as we see it in the sky, but all you need really is a telescope and to look outside of the optical spectrum, and you'll begin to see that the sun is far more complex than meets the eye. Now, the sun itself has intrigued ancient cultures for thousands of years. The sun is pivotal to life on Earth, and as a result of this, ancient cultures have worshipped the sun as a god or a deity. Have some examples here. We have Ra, the Egyptian god of the sun, Helios, the ancient Greek titan, and Huitzilopochtli, who is the Aztec god of war, the sun, and human sacrifice. Now, thankfully, there is no human sacrifice involved in solar physics today, although many mysteries of the sun do remain. But in a way, these ancestors of ours were the first solar physicists, the first astronomers who would look to the sun and would seek an explanation for what they saw with the knowledge that they had at the time. Now, we're going to be beginning our journey today slightly later on than this. We're going to be beginning in the English town of Worcester in 1128 AD. Now, for this exercise, I want everybody to use your imagination, okay? I want you to imagine you are a monk in ancient England in 1128. You wake up one morning doing whatever it is a monk did at the time. You go outside. It's a hazy day, okay? So it's quite misty. The sun is low in the sky. Maybe it's just risen. And as a result of the low sun and the thick mist, you're able to look at the sun without blinding yourself. You should never look at the sun normally. And you look to the sun and you see this. You see these weird objects, these weird black things on the surface of the sun here. And so what I want you all to do, if you're able to on a mobile phone, head to menti.com, enter in this code, okay? I want you to imagine you know nothing about the sun. You don't know what this is. Maybe you do, maybe you don't. Anyway, you're a monk in 1128 AD. You see this. What is your interpretation? Now, at the time, although the monks recorded this in their journals, they weren't really outspoken about it. They didn't write down any interpretation of this. They didn't go tell anybody else in the village. And that's probably because at the time, for someone to suggest that the heavens were changing and imperfect would have been a crime, would have been a sin. And so for that reason, they mostly kept to themselves. Now, in reality, what this was likely something called a sunspot. There's still a chance to head over to menti.com and do this poll if you want to write down some creative answers. I'll visit these later on. But what they likely saw was something called a sunspot. This is a colder, darker part of the sun. They can be pretty large, and you can see them with eclipse glasses sometimes if they're big enough. So this is almost definitely what they saw. But although we've known pretty much since the invention of the telescope in 1610 what these objects were, their origin, how they came about, and how they evolve remained a mystery and a hot topic of debate for many, many centuries. I have here some quotes from some famous astronomers trying to understand what these objects were. So we begin around 1610, after the invention of the telescope. This German astronomer Scheiner, he suggested that these were small planets orbiting closely to the sun. He said these aren't things on the sun at all. They're simply things passing in between us at the Earth and the sun, sort of creating these black dots. But Galileo Galilei was a very famous astronomer. He invented the telescope, actually, among many other things in the solar system. He proved that this wasn't the case. He showed that these objects were rotating and moving with the sun. And so he said maybe they are cloud-like structures in the sun's atmosphere. Just like we have clouds here on the Earth, maybe these are clouds on the sun. And for a while, this was the accepted answer of what sunspots were. But then William Herschel came along. Now, William Herschel was a very accomplished man, a very famous astronomer. He was Astronomer Royal at the Royal Observatory Greenwich, and his most famous discovery was the planet Uranus, so the 8th planet of the solar system he discovered. And he said that these weren't clouds at all, but these were sort of openings in the sun's atmosphere, revealing a cooler surface underneath. Now, this isn't miles away from the truth. They are colder parts of the sun, so he got that right, and they are low down in the solar atmosphere. So at a glance, it seems like he was on the right line. But if I complete the quote here, what he actually said is that these are openings in the sun's luminous atmosphere, allowing a view of the underlying cooler surface of the sun, ... which is likely inhabited. So this is a man, William Herschel, one of the most accomplished, famous astronomers of his time. He believed there were aliens on the surface of the sun, which nowadays just seems a ridiculous claim to make. And I love this. I think it goes to show you can be right about many, many things, but still be embarrassingly wrong about other things as well. But the mystery of sunspots continued and just deepened really in the year 1859 when this guy came along. Now, this is Richard Carrington. He is a part-time, he's not alive, obviously. Richard Carrington, he was a part-time astronomer and a part-time brewery owner. Okay, so a great combination. I feel like he would approve of events like this one, a Pint of Science. And what he would do is he would go outside and he would draw sunspots every day, basically. It was almost a hobby. And he went out one day, drew this quite complex sunspot region here, and he noted 2 white flashes, which lasted just for a couple of minutes in the very center of this sunspot. He recorded this, didn't think much of it, but that evening, the northern lights were seen all the way down from the North Pole, all the way down to the tropics. So the tropics, that's Southern Europe, the Caribbean, places which had never seen the northern lights before, suddenly saw it on this evening after witnessing this white flash in the center of this small sunspot. Now, what puzzled people even more and what deepens the mystery even further is that telegraph machines, okay, they didn't have much technology at the time. They did have telegraph machines. Telegraph machines were recorded to receive messages and send messages even when they were switched off. And machines which were switched on were reportedly sparking and catching fire. Now, nobody had any idea at the time, and not many people even put 2 and 2 together. How could this small flash on the sun cause all this havoc here on the Earth? Now, the actual answer wasn't really understood for about another century, but unbeknownst to people at the time, the answer was actually included in an observation in the very next year. They just didn't know what they were seeing at that point. So here in 1860, there was a solar eclipse, so the moon passes in front of the sun, and when that happens, the sun's surface is blocked, so you can see the fainter solar atmosphere, which normally you can't see. And it's fairly usual to see sort of these streamers, so these parts of the solar atmosphere streaming out from the sun. But what this man recorded in this sketch, he also noticed you can see this sort of weird, swirly spiral pattern here on the bottom right corner. Now, this looks a lot like modern images during eclipses, such as the one in 2020, of something called a coronal mass ejection, which is a type of eruption from the surface of the sun. So a bit of a hint as to what might have been going on, but at the time, they had no idea. And these things move over the course of hours. So in a 2-minute eclipse, it would appear stationary, even though it was not. Okay, so let's have a look at some sunspots in some modern instrumentation. So here on the left, this is the sun as it appears in white light. This is what our eyes see, and these are some dark sunspots here. on the right, this is the sun taken in ultraviolet light. It's not the same time, so the spots don't match up, but these bright regions here are found above these dark sunspot regions. And these are called active regions. And you can see here loops of plasma, which is the material making up the sun's atmosphere, sort of following and moving above these active regions. So the question is, what is this? What's going on? Now, before I move on and tell you what's actually happening, I think we can head over to the results from the Mentimeter. So if the host is able to switch over the displays for me now. Fantastic. Okay, so this is what you thought in the mindset of a 1128 AD monk. What was going on? Okay, well, we've got an eye in the sun, a compass, the devil, a portal, a hole, a sun's nipple. Okay, that's very interesting. A lunar eclipse, a black hole. I wonder if monks knew anything about black holes at the time. God, maybe hell, sun disease, sun people. Okay, cool. Some very creative answers. I like it. Great. Now, if we head back to my presentation. Now, what was actually happening? Something far less exciting than the devil or a sun nipple. The actual cause of sunspots is something as simple as magnetic fields. Now, magnetic fields, a force we will learn about in school, is the reason we have sunspots. It's not the gravity, despite the sun's enormous mass. It's not nuclear fusion, despite that powering the sun's core. It's magnetic fields. Now, magnetic fields, as you may remember, very simply, you can imagine a North Pole and a South Pole and magnetic field lines moving between them. If you have magnetic material, such as iron filings, another experiment you might have done in school, these iron filings move and align themselves to this magnetic field. That's exactly what happens on the sun. These sunspots or active regions, they are magnetic. They have north poles and south poles, and plasma, the sun's material, feels this magnetic force and flows along these magnetic field lines. Now, here on the Earth, we have a magnetic field. Okay, it's pretty simple. It's got a north pole and a south pole, something we call a dipole. But the sun's field is far more complex, far more chaotic. As I said, active regions, sunspots, have regions of north and south, and the sun's surface could be littered in these regions of north poles and south poles. So a very complex and a very chaotic field. And what can happen is because the sun rotates at sort of different speeds over its surface, it doesn't move all as one like the Earth does, is parts of these magnetic fields can become twisted and tangled and get compressed together. Now, if I have two bar magnets and I stick two north poles together, okay, those two north poles are going to want to repel each other. And what's happening here is if I push them together, I increase something called the potential energy, the magnetic potential energy. And as I let go, that potential energy that I created is converted into kinetic energy as these magnets push each other apart. And this can happen on the sun too, except in this case, these field lines don't always have the opportunity to repel one another. And so what can happen in a very complex system is these field lines do something called magnetic reconnection. These field lines reconnect into a lower energy configuration, and this potential energy is released as heating of the plasma, particle acceleration, light from radio waves all the way across the spectrum to gamma rays, and kinetic energy sometimes of the eruption as well. Now, what does this look like? Well, here in a computer simulation, it looks something a bit like this. But on the sun, this emanates itself as a solar flare. A solar flare is just a burst of this magnetic energy on the sun. And there are two examples here, both from September 2017, a few days apart. This is the same region rotating to the edge of the sun. And these are the two events actually that I actually study for my own research, trying to understand these solar flares, trying to understand the processes that lead to their formation. And so ultimately, in the long run, scientists can predict solar flares for reasons I'll explain later is quite important. But sometimes, okay, sometimes an eruption is more than just a solar flare. A solar flare is the reconnection of these field lines coming together. But sometimes, as these field lines reconnect, it's almost like you're cutting the tether to a larger structure sitting above where your reconnection has just happened. Almost like if you cut the string to a balloon, your balloon is going to float away, and the same thing happens here on the sun. If I have reconnection under a larger, complicated magnetic structure, that structure will erupt as a coronal mass ejection. You can see it here very quickly erupting from the edge of the sun. This yellow grid is the size of the sun. So in a matter of minutes, an hour maybe, this structure expands to several times larger than the sun as it hurls off into space. Here is another movie of that. This one looking at the sun's disk. This is a very famous eruption, quite often used in talks, but beautiful, as you can see. And you can really see the complexity of this as plasma is just hurled out into space, as well as sort of scattered across the sun's surface as well. And for scale, this tiny blue dot up here, that is the size of the Earth in comparison to the sun. So you can really see how big these eruptions are. But sometimes these eruptions are actually directed towards the Earth. This image or collection of images was taken by a spacecraft called Stereo. These launched back in 2006, I think. They sent one in front of the Earth, one behind the Earth, and over time they sort of spread out around the Earth's orbit. So this one is almost behind the sun, sort of looking back at the sun and the Earth, which you can just about see a halo from the Earth over here. The Earth is about where my pointer is now. And you can see this coronal mass ejection erupting through the solar system. This is Mercury, this bright dot down here. And as you can imagine, if this thing hurls towards the Earth, something might happen. Okay, you can see this is a large enough object to not just pass by without having any influence whatsoever. But thankfully, here on the Earth, we are protected. We're protected from the worst of this stuff from the sun, okay? And we're protected by all things by the Earth's magnetic field. Our own magnetic field repels away these coronal mass ejections, or the worst of them, which themselves also have a magnetic field. But sometimes, if an eruption is strong enough, it can actually penetrate the outer layers of the Earth's magnetic field. And I hope you can see from this very simple simplification of the actual process, if an eruption is strong enough and it penetrates through the first three layers of the magnetic field, it is then free as it hits the magnetic field to spiral down before it reaches the upper atmosphere of the Earth up by the North Pole. And when it does this, when I have very hot, high-energy particles from the sun colliding with the Earth's upper atmosphere, what we get is the northern lights, the southern lights, the aurora, which I'm sure Michel saw a lot of down or up in the Arctic during his expedition. Now, the northern lights is just our Earth's atmosphere glowing as it gets pummeled by this high-energy particles from the sun. And you can also hopefully imagine from this that the stronger the eruption, the further through it will penetrate. And so when it follows these field lines down to the atmosphere, the further south the northern lights will be, or the further north the southern lights will be. And that's why in very large solar eruptions, such as the Carrington event back in 1859, the northern lights are seen very, very far south. But not all the impacts from the sun are as harmless or as beautiful as the aurora. There's something very real, something fairly serious called space weather. Space weather is the effect of the Earth, our technology, and the near-Earth environment from stuff from the sun. That's what space weather is. Very different to terrestrial weather, which is what space scientists call regular weather here on Earth. Now, space weather events happen all the time. Most of them we don't really notice as ordinary people, but if you're a specialist user of certain technologies, you care very much about these events which happen sometimes daily in active parts of the sun. Space weather sort of breaks down into different aspects. We have high energy radiation, okay, which can be harmful to people. We're protected on the ground, our atmosphere shields us, but if you're an astronaut in space or a passenger on an airline, you are potentially vulnerable to high radiation. It's not the amount that would kill you, okay? But if you're an astronaut, you could be receiving the equivalent of a chest x-ray every few seconds. If you're prolonged there for a long period of time, you're increasing your risk of certain types of cancers and so on. But the main type of space weather actually results not from the high energy particles, but surprisingly from the magnetic field traveling with this coronal mass ejection, traveling with this bubble of plasma. Because this coronal mass ejection has its own magnetic field, as this magnetic field passes over a satellite in space, or even the power grid here on the ground, as you change the magnetic field over this metallic object, what you do is you create a current, you create an electrical flow through the metal object. Okay. Now, if you are a spacecraft which is already turned on and producing electrical signals, what you don't want is another electrical current coming along and fusing your device. That's not good for anything. You can picture it like if you flick your light switch too many times. If you change the electric field in your light bulb too rapidly, you're going to fuse the electronics in that bulb. And the same thing can happen in satellites during space weather events. You change that electric field and you can severely damage them. And in the worst case scenario, even here on the ground, your power grid, okay, could be damaged too. And this is what happened in that Carrington event back in 1859. The magnetic field from this bubble from the sun created a current in the telegraph machines. And so ones that were switched off would send signals that are being powered by the sun. And ones that were already switched on were flaring, sparking, and causing fires because you had fusing of these metallic objects. Now, as I mentioned before, a lot of the time, we don't worry about this. You only need to care if you're a satellite operator and you need to switch off and on your machine or change your orbit slightly to avoid it, so on and so forth. But occasionally, every decade or so, there are much larger events which do affect us here. For example, back in 1989, I think, 1989, there was a very strong solar event, and Quebec, okay, the province in Canada, on the East Coast, containing millions of people, had a power outage lasting 13 hours. Millions of people without electricity for 13 hours as a result of this space weather event. And in a worst case scenario, in the largest solar storm, such as the one back in 1859, that we haven't had one that large since, it's predicted up to 15% of satellites could be damaged temporarily, maybe, or maybe even permanently, due to a strong space weather event. And you'd have localized power outages here on the ground too. Now, as a result of these things, space weather was added to the National Risk Register way back in 2011. And it's on that risk register 2 levels, I think, below a global pandemic, to give you some context there. It wouldn't be harmful to people necessarily, but can cause, or is predicted to cause, billions of dollars worth of economic damage worldwide, rivaling that of sort of the worst hurricanes and tsunamis. Just that economic cost is spread rather than localized in just one location. Cool. Okay, so that pretty much wraps up the end of my talk. I hope I've got across the idea that although we've learned a lot about the sun in recent decades, there is still a lot that we don't understand. Understanding the causes of space weather is very critical for us to really get to grips over the next few years or so. Because as I say, the sun is not harmless. Space weather does have the potential to disrupt our technologically dependent lives. Thankfully, we are prepared. A lot of scientists worldwide are studying the sun, like myself, or actively forecasting the sun, watching it 24/7, waiting for these eruptions and taking actions accordingly when suitable. So with that, thank you very much, and I'll switch back to the host now, and I welcome any questions. Thank you so much for coming.
That was fantastic, Ryan. Thank you. And so interesting to see what, we think is mythical and magical explained with magnets and science. Very fascinating. So if you have questions for Ryan, please put them in the comments section now, and we'll pick them up very shortly. So while we give you some time to put in some more questions, I'm going to hand over to Nick to see what our poll results on our David Attenborough question has revealed.
Thank you, Vino. So we can see that a lot of the people has put Metapecies Attenborough, and a lot of them has put Paleosaur Attenborough's Canterbury. Sorry about the pronunciations. I struggle with these a lot. And another very popular answer would be the Electrotectus Attenborough. So surprisingly, most people got the right answers because these three are actually the correct answers. So I think we should put our hands together for the people who joined. It's super impressive, and we did not expect this at all. So Vino, which is your favorite species out of the three?
Well, so I am from Australia, so I'm going to have to say that the Metapecies Attenborough is my favourite. The Metapecies Attenborough is a type of fish from Western Australia, and Metapecies is Latin for motherfish, which refers to its unique ability to have an unborn embryo inside the mother. So unlike most fish that lay eggs, it gives birth to live young, which is very interesting. The other correct answer was Plesiosaurus attenborosaurus conibere, which is a 5-meter long extinct species that was found, the remains were found in Dorset in England, and the species is thought to have been destroyed in World War II. And the final correct answer that most of you got was Electrotectus attenborough, which is an extinct locust found in the Dominican Republic. And interestingly, they were found in a collection of the gemstone amber, and were named after this. So electrum is Latin for amber, and tetex means grasshopper in Greek. So well done for all of you that got that right. A tough one to answer and pronounce for your hosts. So congratulations. So let's move on now to questions for our hosts. So a few for Dr. Tsamados to start with. Nicholas, if you want to lead on those.
Yeah, sure. So we have got a lot of questions coming in, and some of them are answered. But so I think we can start with Becky's question. So Becky asked, how long does it take to plan an Arctic expedition?
Thanks, Vino and Nick. So it's an international expedition. It's about 200 million in terms of pounds. The cost is quite massive. It's probably the biggest ever Arctic expedition. So this one took several years to put together, to get the funds, to plan it. I would say 10 years in the making. Yeah, this particular one. A normal expedition might take, more down to a year or something like that. But this one was particularly big. I saw another question. Maybe I can take, or I'll leave it to you. But I saw one that was.
Go for it.
Yeah, I'll go for it. So there's a question from Mike. Is the sea ice loss reversible? He wrote, is the sea loss reversible? But that's a really good question, because people often talk about tipping points and they use them a little bit too loosely. So a tipping point is a change that is, in a sense, irreversible. So sea ice, technically speaking, is not irreversible. So if we were to cool our planet again and not warm it up by 2-3 degrees and go back to what it was 100, 200, 300 years ago, then sea ice will progressively grow again. That's the latest research. This is in contrast, for example, with land ice, and you have cataclysmic, collapse of the ice shelves. That these are, in a sense, irreversible. But that doesn't mean it's not a problem. But it's not necessarily irreversible.
And do you have plans for a further expedition, or what's the sort of trajectory in terms of following the further ice loss?
Yeah, we're talking with our group. I mean, not this kind of scale, of course, but we have the group lead here, Professor Strover. We have a radar that we want to deploy to measure the penetration in the snow of the radar. So we have several expeditions planned, and my name has been mentioned, so I'm keeping my fingers crossed for a follow-on trip in the Arctic. This one will include aeroplane trips, landing many times on the sea ice. I don't know if I will be able to take it, but I will try it.
Any room for a solar physicist on your expedition?
I'm sure we can look at the, what you call them, the
and a neuroscience
auroras. We can check together the auroras, right? I saw some of them.
Definitely get you back on Pint of Science to show us those videos. That'd be fantastic. So Ryan, Arjun asks you, what precautions have we taken so far to prepare for high energy events?
Sure, yeah. Thanks, Arjun. So there are a few groups around the world that actually monitor the sun and watch its behavior 24 hours a day, 7 days a week. So just like regular weather forecasters, there are space weather forecasters as well. So what they are good at is seeing an eruption happen on the sun, okay, and sort of predicting roughly when that will arrive at Earth and how strong those effects might be, okay, because it takes about 16 hours to a couple of days for that eruption to hit us. What we don't know and what we're not very good at is seeing a sunspot and knowing when it's going to erupt. So that's sort of the next steps that need to be taken. But yeah, to answer your question, there are a few groups in the world. Our most local one is actually down at the Met Office. So as well as regular weather, they do space weather. They look at the sun 24/7. And it was actually, I did a summer internship there during my undergraduate degree, and that's how I got into the whole solar physics, sun stuff to begin with.
Oh, great. That's really interesting. We've got another one for you from Photo Tote Bag. When we see the northern lights, are we seeing the sun particles or are we seeing the energy's effect on our own atmosphere?
Yeah, so the stuff coming from the sun has quite a low density, okay, but a very high energy. So what we're seeing, it's not the particles from the sun itself that we're seeing, but as these very high energy particles hit our more dense but colder atmosphere, okay, that causes our atmosphere to glow. So as you said in the second part of your question, we're seeing our atmospheric particles glowing, but only after sort of receiving the energy from those particles from the sun. Yeah, great question.
So I see that there's a question coming in from Michel from Eve. She asks if how cold was it? I think she's meaning the field trip. And how do you manage to perform experiments in such low temperatures?
Yeah, I was a bit worried about this because I'm Greek, remember? So yeah, minus 20 degrees for me was a bit unusual. So it turns out if you're in a very nicely heated Russian icebreaker and you go out for less than a few hours at a time, it's perfectly comfortable. But I also discovered that if you go out with a t-shirt and not much on, after 10 minutes, you want to go back in. So that gives you a scale of... So I was going to ask Ryan, how long can you stay at, say, 80 degrees temperature? Yeah.
That's really interesting. Were there any injuries, any frostbites or...
I mean, we had amazing equipment from the Germans, the Alfred Wegener Institute. There's a poor guy who slipped on the deck and broke his leg. That was the biggest injury. And actually, considering the day we saw the ice for the first time was bar night. So there was a combination of beer and frozen deck that was a little bit dangerous. And I think we were very lucky to not have more broken legs. Actually. So, yeah.
That sounds like a fun field trip.
Yeah.
How can you use your data to predict future patterns of melting? And can you use your data to detect how the ice melting is affecting the polar bears and the life out there? I
mean, your safest best bet is to use a climate model because it models all the physics. So this is what these general climate models are doing. They project via physics and via solving the equations of physics how our planet will warm and how the sea ice will disappear. And the projection, to answer the question I asked, when sea ice will disappear entirely in the summer is about mid-21st century, but it could be plus or minus 10 years, and it depends how you define it, of course. So yeah, and the data constrain the model and allow you to improve the models and give you a sense of the state of the ice already. And in a way, it has already entirely disappeared, depending on how you define it, essentially.
And for Ryan, Dude, Where's My Apple asks, are there patterns where sunspots appear similar to an equator?
I thought, dude, where's my apple was the question for a start. I was like, I don't know, mate. Are there patterns of sunspots? There are patterns of sunspots, yeah. So for various reasons that we partially understand, the sun actually has about an 11-year cycle of changing sunspot activities. So at sort of the minimum of this cycle, there are no sunspots. Sunspots are very rare. Maybe occasionally you'll have them dotted around the equator. But at solar maximum, we have maybe 10 or so sunspots on the sun at any one time, and they spread from the equator up almost towards the poles. So to answer your question, it depends where in that solar cycle you are. They're either compressed very close to the equator or they're spread out over the surface of the sun.
Very interesting. So, I mean, I think you've already answered some of the questions that we can't really predict when the next event's going to happen. But, you know, potentially it could affect the national grid, etc.
Yeah, so it's sort of like predicting earthquakes. So you can sort of say there's a chance this will erupt every 100 years, or there's a chance this massive earthquake will be every 100 years, but you can't say for sure it will happen on this date. And just like earthquakes, it's to do with the buildup of energy, right? So in earthquake, you have buildup of these tectonic plates that eventually release and you have your earthquake. Same on the sun with these magnetic fields. So what we don't know is why sometimes this energy builds up just a little bit and we get small earthquakes or small flares, whereas sometimes this energy builds up without eruption for a really big earthquake or a really big flare. So there's lots of parallels between the two in that regard.
Okay. We've got a question for you from the audience. How strong are the magnetic fields, and how are the field lines measured?
Yeah, good question. So how strong are the fields? So I guess the best real way to put that is in a sunspot, the field's about 1,000 times stronger than the Earth's magnetic field. So pretty strong. And the way we measure them, the way we measure field strength, it's pretty complicated, but with modern telescopes, you can measure certain sort of wavelengths of light that are emitted that vary depending how the magnetic field is, essentially. So that's how we measure the actual strength, but it's fairly easy from looking at the sort of imagery that I saw you to see, at least qualitatively, where those magnetic fields are, because this plasma, this stuff from the sun, has to flow along these field lines. If you see it flowing in a certain way, you know the magnetic field is going in that same direction.
Okay, very interesting, very complex. You know, both of you have a fantastic ability to explain complex science terms in ways that we can understand. Well, thank you both speakers, and over to you.
Yeah, thank you both speakers, and also our brilliant UCL Planet Earth team that put in a lot of effort behind the scenes. We look forward to seeing you next year. Good night and goodbye.